Everyone. We are from Group J. We are we are going to discuss about the case study of biomedical dynamics of biomedical engineering on smart neckbands. So let's start off with our group members. So here are our group members. We have 5 people we will be presenting today. I will be presenting. My name is Kamal, and I will be presenting on the introduction and the background. Now let's move on to the contents that will be discussed today, which is the introduction and background, the smart neckband system, literature review and objectives, methodology and mechanical analysis, results and discussion, and also the applications and conclusion. So let's start things off with the introduction. So poor posture can bring a bad impact on the musculoskeletal health. It brings neck pain and discomfort to the neck, and especially for older people. And with the rise of digital devices, many people suffers from neck pain because of poor posture habits and also neck sprain. So therefore, today we have a smart neck bands which helps in detecting the angle of the neck from having a bad posture, and also give feedback to us so that we can correct our posture. So in this study, we'll be asking about the importance and the potential of this ergonomic assisted devices and its relation to dynamics. Now let's move on to the background of the study. Why does posture matter? With the rise of technology, people have been using their phones for too long, which also results in a forward head posture, which is slouching. This is this causes an increase in the cervical load, especially the head is quite heavy, around 4 to 5 kilograms, more than 5 kilograms, and it can cause neck pain and muscle fatigue. So therefore, we decided this study because we want to investigate about the smart neckbands which helps in correcting posture.
Okay, I'm gonna talk about the working principle of the upright go-to device. So the first one is the device detect the posture angle, and then they compare it with the reference posture. So then it identify any excessive slouching, so that they can trigger any vibration alert, so the user can fix their own posture. So the dynamics principle of this device is they have two advanced sensors, which is the accelerometer and the gyroscope, which continuously monitor any spinal alignment. So unlike braces that immobilize and give passive support to the body, the upright go-to encourages the active correction. So the device auto-adjusts during use, ensuring accuracy across sitting, walking, or any physical activity. Okay, I'm gonna talk about the literature review. So the cervical spine consists of 7 vertebrae, C1 until C7, so that supports the head and allow neck movement. In a neutral posture, the load on the cervical spine is relatively low. However, when the head bends forward during slouching, and the moment acting on the neck increases due to the larger moment arm. So this increases the loading that can lead to muscle fatigue, discomfort, and long-term neck pain. So to address this issue, the smart neck bands and posture monitoring devices have been developed. So these wearable systems use sensors to detect neck position and movement in real time. For example, the upright go-to device, which provides vibration when it detects any poor posture. So in the previous studies that shown these devices can improve posture awareness and help reduce cervical strain. However, most research focuses mainly on posture detection and sensor performance. There is still limited analysis how these devices affect the kinematics and kinetics of neck movement. This is our objectives. First one is to understand the application of engineering dynamics principles in biomedical wearable devices such as smart neckbands. Secondly, to examine the role of dynamics in posture monitoring, movement analysis, and rehabilitation systems. The third one is to explore the biomedical applications of smart neckbands in healthcare, including posture correction, patient monitoring, rehabilitation, and activity tracking. So the fourth one is to relate the concepts of kinematics and kinetics to the functioning and performance of smart neckband devices.
To analyze slouching motion, we modeled the human upper body as a rigid body rotating in the sagittal plane. This is known as a 2D planar rotational model. The pivot point is fixed at the C7 and T1 joint, which is located at the base of the cervical spine. We treated the head and upper torso together as a one single rotating body. As shown in figure 4.1, the slouching angle, theta, increases from the healthy upright reference position of 5 degree up to a maximus of 25 degree. All motion is restricted to the sagittal plane, which makes this system suitable for both 2D kinematic and kinetic analysis. Moving on to the free body diagram or FBD, the FBD was drawn at the worst case position where theta equals 25 degrees. Three main forces act on system. First, the body weight, W equals mg, acts downward through the center of mass, creating a gravitational moment about the pivot. Second, the erector spine muscles forces, Fm, acts along the posterior neck to counteract forward flexion. Third, the reaction forces Rx and Ry act at pivot point O to maintain equilibrium. Since slouching happens gradually, we assume quasi-static equilibrium at each posture angle. This gives us three equilibrium equations: the sum of forces in x equals 0, giving Rx equals 0, the sum of forces in y gives Ry equals mg, and the moment equation about O gives the relationship between muscle force, body weight, and the slouching angle. And lastly, six assumptions were made to simplify the model. The head and upper torso form a single rigid body, and the C7 and T1 joint is modeled as a fixed pin joint allowing mainly sagittal rotation. All motion is limited to 2D, so lateral bending is excluded. Slouching is treated as quasi-static, meaning inertial effects are negligible. The center of mass positions remains constant, and the erector spine forces acts at a fixed angle relative to the spine. Based on these assumptions, the equations of motion were derived for kinematics. The angular displacement follows theta equals theta 0 plus omega 0 t plus half alpha t squared, with angular velocity and acceleration obtained by differentiation. For kinetics, the Newton-Euler equation gives the sum of moment about 0 equals I-O times alpha, and together, these equations allow us to calculate the angular displacement, velocity, and acceleration at each slouching angle. Thank you.
Next, we'll be discussing about the kinematic analysis. As you can see here, the table shows that the theoretical data that were generated to show the dynamics and kinematics relationship with the device. The device measures the component in dynamics and kinematics. As you can see here, if this is like an example we took from a person who play games most of the time. So starting from a 5 degree of healthy posture angle, this person have 5 degree of healthy posture angles, and if the game was intense, and they are sitting on a chair, so they will tend to move forward. Their head will tend to move forward, and it's starting from 5 degree of this is like the normal posture angle of neck, and then the game was intense, and then they will move 10, 15, 25, and then 20 to 25, and this is like the angle. um Each angle creates two elements that are very important in this topic, which is the time taken for the slouching, and then the angular velocity. Because these three things, angle, time taken, and also angular velocity, is like the main component of how the device works. Because the device measures these three things to um, initiate the vibration to remind to that individual whether that they are slouching too much or not. As you can see here, the angular velocity starting from 0 to 0.6982 increases significantly, and then it decreases substantially 0.5236, and then lastly 0.2182. Even though the angular velocity decreases substantially, the device will still vibrate because the angle, this slouchy angle is too much. It is like beyond from what it was set at in the first place. According to the settings on the device from the previous table of the individual who have 5 degrees of healthy posture angle, then the device will have a normal response if they are slouching within 0 to 14 degrees, and then the device will enter warning zone or monitoring state to measure or predict if that person will move, the motion of the person, whether they will move forward than 20 degrees. The range is 15 to 20 degrees. And lastly, if that person slouching greater than 20 degrees, it will vibrate to remind that, oh, that person is, you are slouching too much. So the vibration will be generated to remind to that person.
As mentioned before, when the slouching angles of the user are at or exceeds 20 degrees, the device will vibrate. This threshold was selected because larger neck flexion angles are associated with the increase of mechanical loading on the cervical spine. As the slouching angle increases, the center of mass of the head and also the upper torso move further forward, increasing the movement arms and resulting gravitational torque. Consequently, the neck muscle must generate greater force to maintain equilibrium, leading to higher strain and a greater risk of fatigue and discomfort. Therefore, maintaining neck flexion below 15 degrees is recommended to minimize cervical loading and promote healthier posture. The upright go-to highlights the biomedical significance of wearable posture monitoring technology in preventive healthcare. By continuously tracking posture and also providing real-time feedback, the device helps users become more aware of poor posture and correct it before excessive cervical strain develops. This can contribute to reducing musculoskeletal discomfort associated with prolonged slouching and support healthier posture habits over time. Furthermore, its ability to monitor movement and provide corrective feedback makes it valuable not only for everyday posture management, but also for rehabilitation and clinical application, where posture assessment and correction are important. And also, the same dynamics principle can also be applied to other biomedical devices, such as smart spinal braces and also shoulder exoskeleton. This technology use movement tracking and feedback mechanism to help improve body alignment, support rehabilitation, and also reduce the risk of injury. This case study demonstrates that engineering dynamics principles like kinematics and also kinetics are effectively applied in the upright go-to for posture monitoring and also movement analysis. As wearable device, it highlights how biomedical engineering supports preventive healthcare by improving posture awareness and also reducing the cervical strain. And its application in posture correction, rehabilitation, and posture monitoring reflects the growing role of biomedical engineering in modern healthcare solutions. That's all from us. Thank you for listening.